Hello everyone. If you're joining me today, we're going to start looking at systems of equations. More specifically today, we're going to be looking at solving systems by graphing. So a fair warning, today we're going to be looking at something that requires or is heavily reliant on graphing linear equations, specifically in y equals mx plus b form. So if you aren't as familiar with graphing, you may want to take a look at some videos online or try to take a look at that before we get started. Otherwise, if you are good with graphing and you know what you're doing, we're just going to jump in here. So let's talk about what a system of equations is, first and foremost. If this is your first time hearing that phrase, systems of equations, it's important to know this. Systems of equations are two or more equations with the same variable. And that's really what it is. When we say systems, it is meant to say, very much meant to evoke the fact that there's more than one. There's a set of equations. Sometimes there's more than two, but most of the time we only work with just two. Some of you might be wondering, well, when are we ever going to use this? Because I know I get that question a lot. More times than not, though, we end up using systems of equations in real life to compare different plans for cell phones, perhaps. If you use AT&T versus Verizon, you have to think about the registration fee of your phones and then think about how much it's going to be per month to text, call, whatever you will. It is totally possible to use systems of equations, although sometimes you might not use it as much as you think. Now, the solution to a system of equations, because reminder, what we're trying to do is solve. The solution to a system of equations, graphically speaking, is a point xy where the two lines intersect. And really, this is what we're going to be looking for today. We're going to be looking for lines that intersect. Now, algebraically, which we'll be looking at in subsequent lessons, is when we find a point x comma y that makes both equations true. Now, really, what does that mean? It means that there's an x and a y that will make both equations equal, so to speak. You want the variables to work in both equations. And if the variables work in one equation but don't work in the other, it's not a point that is the solution. So this is a new idea for us. So as you're already kind of figuring it out, our solutions to a system of equations is going to be a coordinate point. It's actually going to be x comma y. It's not just going to be x equals or y equals like we've seen in the past. It's going to be a coordinate point with an x and a y. Now let's look at this, because types of solutions, graphically speaking, are different from what we'll see algebraically, because graphing is the visual math. It really is. It's how we model and draw lines and see the behavior of these linear equations. So let's see what we've got. When we have intersecting lines, remember that intersecting lines are kind of like this. Suppose I have a line that's going up to the left or down to the right, and then I've got another line that's going to cross it just like this. And it's going up and to the right. Now, where these two intersecting lines meet, and I'll do this in a different color just to highlight it, where these two intersecting lines meet, that would be the solution. And so what you notice is that we have just one solution. And that solution is going to be a coordinate point, x comma y. Now, I know you're already going like, wait a minute. What's he mean there's only one solution? Well, when it comes to systems of equations, because we have two different lines, there's different ways that they can actually compare to one another. There's different ways that they can look on a graph. So it's possible to have three different types of solutions. Obviously, intersecting lines, as we've shown, will have one solution, one point. Now, if you've ever heard of parallel lines, don't forget that parallel lines are lines that run adjacent to each other. They are next to each other and keep going the same direction such that there is no solution. There is no point at which they cross. So when we have parallel lines, the solution is not there. It's non-existent because the lines are never going to cross. These are like two completely different plans that are never going to be the same. This is almost saying Verizon has a much higher registration cost and Verizon has a higher monthly rate for texting. Since there's no way that can overlap with a lower price for registration or monthly cost at AT&T, Verizon and AT&T are never going to be equal. And that's just to throw a real-life example at you. Now, that's probably not true. I just favor AT&T because I have them. Now, suppose that our two equations come out to be the same exact line. Suppose I've got a line going like this. This is my first line. And then for some odd reason, I have another line that just goes right on top of it and is going in the same direction and it's at the same place. Well, when the equations and the line turn out to be the same, we actually say that there are infinitely many solutions, or there are an infinite solution. There are infinite solutions. And so we draw this sideways 8 to resemble infinity. When it's the same line, they're always going to be the same points over and over and over and over. So what does solving systems by graphing look like? What are the steps involved? Now remember that I said this is going to be heavily based on graphing. So again, if you're not familiar with this, make sure you go try to figure it out, watch some videos, all that stuff. First things first, we need to talk about steps. We can always break a mathematical process down to steps, which is actually really nice. It can help us see the process and think about the steps we need to take. It's a problem-solving process. First things first, we have to account for the fact that our equations may not always be written in slope-intercept form. If that's the case, we need to rewrite the equations in slope-intercept form. Or I might say y equals mx plus b. Hopefully you recognize that that is slope-intercept form. I think writing it here is going to be more important because we'll be able to actually take an equation that's not of the like and try to get it so that it looks exactly like this. Now obviously when we rewrite the equations in slope-intercept form, we are then going to want to graph the line. And remember, to do that, all we do is we pull out the y-intercept and plot that first. Then we use the slope to find a second point, and we graph the line by drawing a line through those points. After that, we just have to identify the solutions. So really, if you think about it, for those of us who are familiar, I should say solution or solutions, because there might be more than one, there might be just one. But as I was saying, for those of us who are familiar with graphing equations, this is essentially systems of equations are graphing equations times 2 and then just trying to figure out whether they intersect or not and what the solution is. So we're going to look at these two examples, and hopefully this will be enough to get you started on your way. So I'm going to start out by graphing these two equations in number 1. Y equals x minus 8 and y equals negative 2x plus 1. I'm going to graph the first equation. And the first equation, my y-intercept is negative 8. So I'm going to start at the origin, go down 8. 1, 2, 3, 4, 5, 6, 7, 8. I don't know about the rest of you, but I am a counter. I like to count my points. Now notice that the slope here is 1. There's no number in front of the x, so we always call it 1. And what this means is slope is going to be 1 over 1. So I'm just going up 1, right 1, up 1, right 1, all the time, just like this. Now to get a clear line, to get a straight line, I'm going to pull out my handy-dandy ruler here in Explain EDU. And I'm going to set this up so that way I draw my line perfectly. I am almost OCD like that. Not entirely, but enough that I would like to have as straight a line as possible. Now I'm going to change up my colors as I go to do the second equation. And the second equation is y equals negative 2x plus 1. Well, the y-intercept is positive 1, so I draw my point here. And the slope is negative 2. Now this is going to become negative 2 over 1, which means I'm going down 2, right 1. And I do this each time. I'll draw 3 points this time, leave it at that, and then I'm going to position my ruler, my straight edge, so that way I can draw my line perfectly. Got a little bit of an oops there, kind of a happy accident for those of you who are familiar with Bob Ross. I know it's not the same thing as painting, but I find it enjoyable. Now, as we look at this, hopefully, remember that after we've graphed the lines, and we have graphed the lines, we need to identify the solution. And hopefully you're already looking back up, because we can look at our examples up here and say, does that match? Does that look like anything I have up here? And hopefully you're saying, yes, it does. When I look at this, I say, hey, I see that they intersect at this point here. So now we have to identify that point. I'm actually going to erase some of my stuff. And I notice, remember that this is going to be, since there's an intersection point, our solution is going to be a coordinate. So I have to identify x and I have to identify y. So let's see, how far over is that? 1, 2, 3. Kind of like counting slope, but backwards. So the x coordinate is going to be 3, and then I have to go down 1, 2, 3, 4, 5. Because I have to go down 5, that's going to be a negative 5. And that's the solution to my systems of equations. I have the equations in y equals mx plus b. I graph the lines. When I find that intersection point, I found that the x coordinate is positive 3, and I had to go down 5, so my y is negative 5. Let's try to do the same thing, but with number 2. So y is equal to 1/2 x plus 9. Let's start with that. All right, so the y-intercept is 9, so I go up 1, 2, 3, 4, 5, 6, 7, 8, 9. There's my y-intercept. Now I use the slope to find another point, and the slope is 1 over 2. Because those are both positive, that means I'm going up 1 and to the right 2. Now, I don't really like that amount of space that's between those 2 points, so I'm going to go for another one, and I'm going to work backwards. And remember, to work backwards, we just have to flip the direction of both. So instead of going up, I go down, and instead of going right, I go left. So down 1, left 2. And I'm actually going to keep on doing this, so that way I have as many points as I can, because the amount of space between each of those points is really, it's not that much. And I want to have the most accurate line I possibly can. So now I'm going to line this up using my straight edge. Recall that you don't have to have a ruler to graph great lines. You can use just a straight edge, such as your student ID, or I used a clipboard the other day. Use whatever's available to you. Now, if we go and we want to look at the second equation, y equals negative x plus 6, let's see. 6 is my y-intercept, so I'm going to go, actually, if this top one was 9, I just need to go down 3. So 8, 7, 6 is right there. Now, the slope of the line is negative 1. You see that? There's no number in front of x, so it's negative 1. So what this means is negative 1 over 1, and I'm going down 1, right 1. So down 1, right 1, down 1, right 1, down 1, right 1, and so on. I think that'll be enough points. I'm going to turn my ruler, my straight edge around. I'm going to set this up so that way I can get the most accurate graph I possibly can. And that actually looks really good. Okay, now looking back at our examples up above, how many solutions does this have? Hopefully you're saying just one, and that would be correct. The one solution occurs right there. So now, knowing that my solution is just one and it's a coordinate point, I have to figure out what that coordinate point is. How far over, left or right? Because I have to find the x-coordinate first. Remember that I always find the x-coordinate first, then the y. So it looks like it's over just 2. But because I'm going to the left, that's a negative 2. Then if we go up, 1, 2, 3, 4, 5, 6, 7, 8. Oh, we went up 8. So the y-coordinate is 8. Our solution to this system of equations is negative 2, positive 8. Hopefully this is enough to get you started. Really, it's mostly graphing equations, and then if you have to identify the solution, you just look back at our 3 examples up here. As always, if you have questions, you know where to send them. Otherwise, have a great day, everyone.